All we've looked at so far is black dots and red stuff, but we're dealing with electric circuits, so presumably the black dots and the red stuff actually mean something. In this part, we're only going to look at the black dots, and in the next part, we'll look at what the red stuff means. So what do the black dots mean? The easiest way to think of the black dots is as a clump of millions and millions and millions of electrons. But there's a little catch, and we'll come to that catch a little bit later on. In fact, each black dot represents 1 coulomb of charge. Electrical charge is measured in coulombs. In order to have enough electrons to make 1 coulomb of charge, you need about 6 billion. So where do these electrons actually come from? Well, the important thing to remember is they don't come from the battery. The electrons are already there everywhere in the circuit because everything is made from atoms and parts of the atom are electrons. So the electrons are already there everywhere in the circuit. They're part of the metal in the wires, in the bulb filament, and in certain parts of the battery as well. This diagram here shows what we might imagine the metal might look like inside the wire. And each of these little round things here, these are meant to be atoms. Notice there's a lot of empty space in between them. And at the center of the atom, you might be able to see there's a tiny, tiny, tiny dot, and that's the nucleus. And you can also see there are these shadowy things moving around here, and they're meant to represent individual electrons. And in a metal, one or more electron for each atom is not connected with the atom. It's called a delocalized electron, and it just sort of floats around like this. So we've got these atoms staying in one place, jiggling about, and then we've got these little shadowy things which are individual electrons. While the circuit isn't connected, the electrons just drift around, but as soon as it is connected, then the electrons start moving like this. And you can see that they bash against the atoms as they move along. So they don't just go in a straight line, they jiggle. And that's why we have our black dot jiggling in our animations. It's actually very difficult to properly visualize the movement of the electrons because you're having to deal with 3 very different speeds all at the same time. If we imagine each individual electron is in a box like this, we see that each individual electron is just jiggling around all over the place. It's not making any progress down the wire. The electrons are moving very, very fast, around about 1% of the speed of light. That's about 4,000 times faster than a passenger jet. When the circuit's connected, then each little box finds out about the circuit being connected very, very quickly, like a ripple. But it doesn't take no time at all. And that, which is called the signal speed, is about the speed of light. Watch what happens when the circuit is connected. You can see this ripple. And then once the circuit is actually connected, the electrons still are whizzing around individually, but they're making very, very slow progress along the wire. And this is really what electron speed's about. There's lots and lots of movement, but very little progress along the wire. So we've said that the black dots are 6 billion free electrons all lumped together. But we said there was a bit of a catch, and we're going to look at that catch now. You may have noticed in our circuit animation that the black dots start from the positive side of the battery and move towards the negative side of the battery. But even though the black dots are already there and start moving everywhere at the same time, they move away from the positive side of the battery and move towards the negative side of the battery. So in that case, these black dots must have a positive charge to be repelled from the positive and attracted towards the negative. Even though it's really electrons flowing in this sense, away from the negative and towards the positive, we imagine that it's positives moving away from the positive and towards the negative. This is called conventional current. With electric circuits, we always imagine that it's conventional current that's flowing, even if it's really electrons. What we do is we imagine getting rid of the electrons and replacing them with these imaginary positive charges instead. So why are we using conventional current? Well, it's because of the history of science. The problem is that the scientists who first worked on electricity didn't really know what it was. They thought it might have been a fluid, or maybe it was different types of particles, but they didn't have any particular idea of magnetism and electricity. And it was only over time that magnetism and electricity were joined together. And so they had to make some assumptions, and one of the assumptions they made was about what sign of charge was flowing. And so they guessed positive. And so all of the laws, magnetism and electricity, were written in terms of positive charge. So we can't just unfortunately rewrite them, because if we had to rewrite the rules for simple electric circuits, we'd also have to rewrite the rules for all of magnetism, and we'd have to rewrite a lot of other stuff as well. So even though we know that it's really electrons flowing in this sense, we're just going to pretend that it's positives flowing in the other sense. So these black dots represent 1 coulomb of positive charge.